Mechanisms in organic chemistry can be really confusing. However, if we find the similarities between mechanisms, maybe they're a bit less confusing, because we know that the first very thing is identify nucleophile and identify electrophile in our mechanism, because we know that that's going to give a start. And then we can think about, okay, is there anything else that can break? Is there any bond that can be formed? So there is a bit more thinking we could do. So I want to compare now two different mechanisms. We'll start with the ketone and the nucleophile, and we start with a anhydride. Okay, so this is acid anhydride and this is a ketone. Both reactive with a nucleophile. Okay, the nucleophile could be a hydroxide, could be something there. Analysis to do. Well, we have a carbon double bond oxygen, so we know that that's normally our nucleophile, our electrophilic center, because we know that the carbon is slightly positive, and this one even more, because as you can see, it's next to two oxygens, so this is going to be even more delta positive. This is one of the reasons why that's actually more reactive. But let's look at the mechanism, like at the same time. Nucleophile attacks these dipoles, so the carbon. And of course, carbon can't have more than 4 bonds, so the weakest one, the pi bond, will break. Guess what? Exactly the same happens here. Okay, because, well, nucleophile, electrophile, carbon can't have more than 4 bonds. If there is a pi bond, that one is the one that will break. So we can think about the intermediate now. Oxygen, it's negative. We still have that same groups attached, but now in this case we have a nucleophile. Let's have a look here. Well, same things. We have the oxygen with the negative charge. We still have this group attached, and we have a nucleophile. Okay, now there's nothing that can break, because we have carbon-carbon single, carbon-carbon bond. They're really strong, but they are not going to break. Yeah, the nucleophile just formed, so it's not going to break back. So the only thing that this can happen is that it's going to react with an H+, which is normally added in the second step of this mechanism. Yeah. But in this second one, there is this bond. And this group, it's a very nice and stable group. The reason of stability is a lot more complex than that. But the thing is just, it's a molecule itself that is pretty stable. And this is what makes this a good leaving group. This is called leaving group. And when there is a good leaving group, instead of reacting with a hydrogen, also the molecule doesn't look good, it makes it so clustered, there's too many things around. The double bond, I would call it the double bond, reforms, and the weakest bond will break. This would happen. So now we have a nucleophile attached here, and this has left the molecule with a negative charge and probably would react with something else. For example, this could react with an H+ to form a pretty stable molecule, a carboxylic acid, as a leaving group. Okay, so these mechanisms are different just because of this leaving group, because actually the first step for both is addition. In fact, this is called addition. This is also called addition.
Oh, I see, and then you got elimination.
Exactly. The second step, we have elimination. So this mechanism, it's called addition-elimination. Well, the first one is just nucleophilic. And this is to distinguish it to the nucleophilic substitution, because essentially this is a substitution, right? Because look, this full group has been substituted by a nucleophile. Yeah. Important, this first one, it's what occurs for aldehydes and ketones. So we'll see reduction, nucleophilic addition. But this is a really important to make esters and to make amide. Okay, because this nucleophile could be an alcohol. Yeah, and this is not the only molecule that it would do. Technically, carboxylic acid could too, but acyl chloride, they have this good functional group. Maybe amides, they could react in the same way because they have this, that could be a leaving group. So anything that has a leaving group would undergo this addition-elimination. And this is an important one for the interconversions between different groups. But the key one to know at A level is for esters and amides. So let's look at one example. So let's look at an example of how to make, well, esters and amines. At the end, it's really similar mechanism. All it changes is the nucleophile. Okay. So let's say again, we have this acid anhydride because it's really clear to see this functional group. So this leaving group. Okay. Let's say we have an alcohol. Let's say we have ethanol. So analysis first. Delta positive, delta negative here. This is also delta negative because, well, it's an alcohol, we know that. Hydrogen delta positive, carbon delta positive, doesn't matter. The one that we care about is the lone pair on the oxygen. Okay, what happens? Well, same as usual. But now let's think about the intermediate, because I know that there is a lot of bonds, so it's important to write it down in a very clear way. That's why I think skills of formula really, really help when we want to scribble out those mechanisms. And if it's written in an exam question a bit too complicated, just try to either see or write the molecule in a way that you can visualize it better. Okay, because what happens now? Well, we still, and it's important to follow the arrows like super carefully. What I would do is, what bonds are still there that didn't break or were not affected? Well, we have this carbon bond. These are the carbon bond with the oxygen, and these are the group. This is unaffected by the curly arrows for now, so we can think about it. Now we can think the others. We definitely, one bond is still there, carbon, oxygen, and then the oxygen, but now the things have changed. So we have the lone pair, an extra lone pair on the oxygen because this bond broke on it. And then actually I would rather write it as the starting of the curly arrows and then think it as a consequential steps. So now we have a new bond with the oxygen, okay, and this oxygen still has this carbon and the hydrogen. Oxygen with 3 bonds, the basic covalent bond, this is going to have a positive charge, while this oxygen will have a negative charge because of these electrons that go on to oxygen. Okay.
Right. Yeah.
Now we can think about the next step.
Stable leaving.
Exactly, stable leaving group. So the carbon double bond will reform. So this will break to form. Again, let's follow the arrows. So we still have these bonds. We still have well, now this one is the new oxygen, right? With these chains like this, okay? With still that H attached, so this one has just come on this side. And then, well, the double bond has reformed following the curly arrows. And then what happened to this one? Well, we have the oxygen with the carbon double bond and this CH3 group, but now it has a negative charge. So guess what happens in the next mechanism? Of course, we don't want to have things that are charged.
So you've got to have something, electrophile.
It's this oxygen will pick up this hydrogen because we know that the oxygen won't stay charged, but it won't
have
the lone pair on it, which means that we will have carbon double bond here, the oxygen is now there, and then we have with the side product, the plus being a carboxylic acid. Okay, so addition-elimination, and as you can see, we have an ester, so acid anhydride alcohol. This will form an ester with the side product being carboxylic acid. Okay,
right, yeah, that makes sense.
An amine, it would be exactly the same mechanism. Yeah, imagine an amine would be like this. Yeah, let's say primary amine, same exact mechanism at the end. Okay, so it's very important to see the similarities, because if you understand the basics of nucleophile electrophile movement, then doesn't matter which nucleophile you have, you can always follow along this arrow and work out the different types, the different products form, and the functional group interconversion.